Hello, hello, it is lecture 10. It is lecture 10. Yes, indeed, it is lecture 10. It is so good to talk to you. We have gone through the basics of physics, the stuff that matters to our lives, to our bodies, to our health, to a biology around us, the motion, why things move, the matter, things that make us up, the solids, the liquids, the gases, the stuff, the molecules, little tiny itty bitty particles, and the energy that's locked into those chemical bonds or held in positions based on gravity and all that good stuff. Kinetic energy, potential energy, energy in food, food calories or kilocalories versus joules and kilojoules and all those kinds of things. And even E equals mc squared. And so now we are ready to start applying these wonderful basic things of physics and blossoming them into the kinds of things that will move you forward as you work on a career, hobby, activity in the medical fields. Ready? Okay, we're going to go right now. If you are a nurse, this is very interesting. If you are a nurse and I ask you, what are the 4 vital signs? You will tell me immediately. It's very quick. It's actually a fun story. I talk about that. I may have talked about it before. Uh, when I spoke with some very intelligent people, like very well trained, highly intelligent, highly degreed, and people went to really rigorous academic programs. And I asked them, what are the 4 vital signs? And they were like, well, maybe like, I guess you take your pulse, right? Like, yeah. And maybe your blood pressure. Yeah, okay. Yeah. But they were like, struggling to figure out what's going on. But I asked a friend of mine who's a nurse, and I've mentioned this nurse friend in the past, and she was like, yep, here are the 4 vital signs: pulse, respiration, blood pressure, and temperature. Boom, bang, 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 like right off the top of her head. And she was like, yeah, and these are great. And I talked to her and she's like, yeah, the physics, all of it is physics. There's a lot of good chemistry. There's a lot of good biology and a lot of good anatomy and physiology in things like nursing. Okay, as a degree, as a career, as an activity. But really, so much of it fundamentally is physics. And it gets obscured by the fact that you're not seeing necessarily where all that physics goes. Well, now you get to see the physics of the heart pumping, the blood around your body, that pulse that you get, from your wrist or maybe from your ankle or maybe from your carotid artery here or wherever they wind up getting the pulse from. Why is that pulse happening? And how do you know that your knowledge of the physics of blood and your heart working can help you understand what to do in this world of medicine? Let's go for it. Remember, this is a physics class, right? So I'm going to leave all the anatomy stuff and the chemistry stuff and the biology stuff to your other classes. I'm just going to talk about the physics of the heart. The typical adult human heart, it weighs about somewhere between a half a pound and a pound. Okay, in terms of mass, it's about 300 grams. All right, so it's about this big, and it just squeezes, and a very complicated squeezing process too, right? You realize, like, if like you got a rubber ball or something, you squeeze the rubber ball and it's got liquid in it, it'll come out, but it's not well controlled, and more water, and more liquids coming in all the time. It's actually a very smooth and sophisticated rhythm, which is really beautiful and fun to look at. But that's not my expertise, right? What my expertise is what's coming out and how fast and how often, because that's physics. And measuring that and understanding that is really, really valuable in work when you're doing, say, something like nursing or other kind of medical profession type stuff. Okay, so let's do that. What is it that pushes, right? We've talked about that before. Force pushes stuff, right? Force, yes, and we know that. And then pressure, right? Pressure is the amount of force over a given area. We've talked about this before too, but why don't I just go ahead and write that down one more time so that you remember this. And then after we go through this part of the lecture, I'm going to point you to the college physics textbook in the OpenStax series so you can take a look at some of this yourself a little bit more, okay? So pressure is force times area, force divided by area. How much force is being spread out over how much area, right? And we've talked about how usually people think of pressure, like in tires, as pounds per square inch, right? Because pounds is actually a unit of force, as you know. It's not a unit of mass, but weight and mass sometimes we wind up mixing up in our brains because we think of ourselves as weighing a certain number of pounds. But we don't think about our mass in a certain number of kilograms as much as we perhaps should. So make sure you know that difference, right? Pounds is a weight or a force, right? And newtons are a force, and you can convert pounds to newtons, but also a mass of a certain number of kilograms will produce a weight of a certain number of pounds or newtons, say if you're at the surface of the earth or something like that, okay? So we like to use newtons per square meter, but you've seen PSI before, right? So units include pounds per square inch, PSI, okay? Or newtons per square meter, also known as pascals. Okay, newtons per square meter or pascals. But there's also a unit which dates back to the olden days when people were first starting about pressure. Okay, and that's millimeters of mercury. You'll see this mmHg. Okay, because Hg is the chemical symbol for mercury, and mm means millimeters. Okay, so the millimeters of mercury is a way of measuring pressure from a long, long time ago. There's a guy named Evangelista Torricelli, okay, who figured out that if he took like a glass tube and filled it with mercury, okay, but made sure that that glass tube had no air in it, and then you just kind of put it upside down in some liquid, and then he just let the air pressure push on this mercury and push it up a certain amount. He found out that air, just the air around us, could push the mercury up the tube a certain height, which is really quite amazing. So he figured out that air pressure could push a column of mercury up a tube a certain height. Okay, and that height turned out to be 760 millimeters of mercury. I'm going to write that down too, because 1 atmosphere, right? An Earth atmosphere is an ATM. Unfortunately, you can't get cash out of this ATM, but that's measured in atmospheres, okay? And what happens is you have all these different ways to describe what pressure is. And so it turns out that in our, I'll put a little extra parentheses around this to match up this parentheses up here. So PSI, pascals or newtons per square meter, millimeters of mercury or atmospheres. And these are all different ways of measuring, how much pressure is going on around you. And it turns out that in our bodies, it is when the heart pushes or crunches, right, does its contraction thing, that is a push, and it causes a push of force through blood vessels. And blood vessels have an area, and there's blood in it. So as it pushes, it presents a certain amount of newtons force per unit area through your blood vessels. So blood pressure is indeed a thing which is force per unit area. See, pretty cool, right? Now, the heart, when it pumps, and I'm taking my pulse here, for example, every time I feel it, poo, 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 what happens is the heart going squish, squish. It's producing a bunch of force that's coming out, and it's translating through the blood vessels to create a certain pressure in an area, okay, a newtons per square meter, and it spreads out all over the body. And then slowly it comes back to the heart with a lower pressure, a steadier pressure, but it is the push, push, push that allows for the blood to circulate through the body. Okay, so every time you feel the pulse, 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 that's the higher end of the pressure. and then the lower end of the pressure is after, in between the pulses. Okay, so that's what a pulse is, right? Every time the pulse, you have a pulse of pressure coming into your body. And that pressure is measured in any of these units, whichever ones you want. But it turns out that for the medical profession, we like to use this millimeters of mercury measure, okay? Just because, Evangelista Torricelli did this a long time ago, and before all the rest of this other kind of formulation came about and people kind of figured out the difference, or not the difference, but figured out like the various ways in which to measure pressure, turns out that that's a really good way. So they did it. And for medical practices, that's pretty much all you do nowadays. You use those numbers. There are other reasons to use other numbers, but let's just use these because you know what? This is the kind of thing that you'll encounter if you are going to be a medical professional. So let me write down the numbers. It turns out that 1 atmosphere, let's do a conversion. 1 atmosphere, that means the air pressure that we are experiencing around us all the time, okay, is 760 millimeters of mercury. Okay, so the column that Torricelli saw go up to the height from the level of the mercury pool up the glass tube was 760 millimeters, which is 76 centimeters, which is about 2.5 feet. Okay, you can try this sometime if you feel like it. It's really quite amazing. If you actually get a true vacuum on one side of a glass tube, you can actually just dunk it in and whoosh, 2.5 feet of mercury will stick out. If it were water, it's even more amazing. It's 32 feet of water. Imagine a column 32 feet high. Wow. If you were an engineer in the olden days, there's something called an artesian well that allows you to get water, pump water, basically using the air pressure to get up to where we are from the ground. The lowest you could go for an artesian well was 32 feet. Because that's the atmospheric pressure that allows you to do it. So 1 atmosphere is 760 milligrams of mercury. It's also 14.7 pounds per square inch. Okay, and it's also about 101,000. It's 101,325 or something like that. But I'm putting it to 3 significant digits. 121,000 pascals. Okay, these newtons per square meter, which are also pascals. Like that. So 101,000 pascals. That's really a lot, right? So the pascal is a really small unit compared to these others. But it turns out that 760 millimeters of mercury is what we use today in our daily lives. So what is that pressure, right? What is the pressure that comes out every time I feel my heartbeat? Push, push. How much pressure is out there? Okay. Turns out that typically when the blood is pumping, when the pulse happens, that blood pressure is somewhere a little bit above 100 milligrams of mercury. And then in the resting time between pulses, the pressure that's sort of residual, that kind of sits around in our arteries as we go forward, right? Boom, on, off, on. The off side is usually a little bit less than 100 millimeters of mercury. That's the pressure, okay? So what happened was that we have these blood pressure cuffs, right? And we can figure out, like using the blood pressure cuffs, if you actually, and then, right? If you ever do that stuff, remember, I'm not a medical professional, so I know how to do blood pressure, but that's not my jam so much. But if you're measuring blood pressure, you get a number, right? That's the number when it has the high pressure. That's the number on top. And then there's a pressure below the lower number on the bottom. So you measure blood pressure, you measure the pulse, right? How many beats per minute? And then you have the blood pressure and a typical, what most people would consider a healthy blood pressure, a human body working at a healthy condition, all right? Human blood pressure at the high end, human body blood pressure at the high end in a healthy person, right, is typically about 120 milligrams of mercury. When the push happens. And then when it's relaxing in preparation for pushing again, the pressure is about 80 milligrams of mercury. So if you go to a doctor's office and the nurse is taking your blood pressure and they say it's 120 over 80, that's your blood pressure, that means that when it's pushing, it's 120 milligrams of mercury above and beyond what we would normally measure, right, in our bodies due to atmospheric pressure and so forth. And then 80 would be the milligrams of mercury after that. So you can figure out, you could make this calculation from 120 milligrams of mercury. How many pounds per square inch is that? How many pascals is that, right? You can do all these kinds of calculations based on these numbers, 120 milligrams of mercury, 80 milligrams of mercury. That's kind of how you do it. So think about this. Our atmospheric pressure is about 760 milligrams of mercury, right? So 120 is maybe 1/6, a little bit less than 1/6 of that atmospheric pressure. And 80 milligrams is a little more than 1/10 that of the atmospheric pressure. So it's only a small fraction. It's a small percentage, relatively small percentage of the atmospheric pressure that we have, but that is enough. In fact, it's necessary to get the blood pumping around our bodies, okay? So that's blood pressure in this case. And then we talk about the heart as it pumps, right? When the heart beats, remember, the heart is about this big, all right? And it's muscle and it's got chambers on the inside. You know that better than I do in all likelihood if you've taken some sort of anatomy and physiology, okay? Any given pump, how much blood actually gets out? Turns out that, well, if you actually do the calculation, typically the amount of blood that gets out is about 70 millimeters for a typical adult human heart. Okay, so the volume of the blood that comes out, I'll just write this down here. Okay, typical volume, and again, every person is different, so you have something slightly different. So you have 70 or so, okay, about 70 milliliters, that is cc, okay, cubic centimeters, 70 milliliters of blood per heartbeat. Each time the heart beats, 70 milliliters of blood come out, okay, come out. And then it is under this pressure, under pressure, sorry, under pressure, 120 milligrams of mercury. That's the pressure that comes out from. And typical human heart rate. What is a typical human heart rate? Anyone know? You can do this experiment sometime on your own. Typically, a healthy adult has a heartbeat of about 70 beats per minute. That's the pulse, okay? It's about 70 beats per minute. That means, what's 70 times 70? Every minute, right? 70 milliliters per heartbeat, 70, remember a milliliter is equal to a cc, right? Or a cubic centimeter. And so if you multiply 70 by 70, that means that every minute, about 4,900 or about 5,000 cc, right? Milliliters of blood gets pumped through your heart per minute. About 5 liters, right? 4,900 milliliters, about 10 quarts. Is that right? No, it's about 5 quarts. It's about 10 pints. Okay, it's about 10 pints. So that means that 10 pints of blood come through our heart typically every minute. About 10 pints of blood gets pumped, 10 pints of blood gets pumped through our heart every minute. That's pretty good, right? Not bad. That's a very interesting number, about 10 pints. Okay, here's the next question. How many pints of blood do you have? Hmm? In other words, if we're pumping 10 pints of blood every minute, is it the same 10 pints of blood? Like how many pints of blood are cycling through to our whole body, right? It's got to go all the way through fingertips, our feet, our brain, whatever, our lungs cycle through in and out, in and out, and then back to our hearts, right? So how much is actually going through us? Another cool question. It's also a physical quantity, right? So let's figure that out. Turns out the typical human body has about 7 or 8% of its mass or its volume as blood. Okay, so that's about how much it is. So if we human beings, a typical human being, let's just use a typical person, say weighing about 110 pounds. Okay, so 110 pounds is about 50 kilograms. All right, so I'll write that down. So for a 50 kilogram person, okay, mass person, now that person, 50 kilograms mass, would weigh about 110 pounds at the surface of the earth. All right. Remember, if we were to get complicated here, we can really say that your weight is different on different worlds, right? So if you want to learn cool stuff about like space medicine, you want to know what your weight is when you're standing on Mars or you're standing on the surface of the moon, I've got a formula for that. But for now, let's just say 110 pounds on Earth, roughly. Person has a mass of 50 kilograms. Okay, and that 50 kilogram mass person, about 7 to 8%. Let's just round it to 8% of the mass is blood, is this liquid we call blood. Okay, about 8% of that mass is blood. All right, well, if that's the case, well, we can figure out how many kilograms of blood this person has, right? And it turns out, multiply 50 kilograms by 8%, which, as you know, is 0.08 when written in decimal form, right? So I will write 50 kilograms times 0.08. That's 50 kilograms times 0.08. Tap it into your calculator, or you can do it in your head, right? The answer is 4 kilograms of blood. Now, a kilogram of water, right, is about 1 liter, okay, just over 2 pints. So 4 kilograms of blood is about 8 pints. Okay, it's maybe like a little bit more, maybe like 9 pints or something like that, but eight is close enough. 8 to 9 pints. It's about 8 pints. So this is a person that has a mass of 50 kilograms or about 110 pounds. Now, for a typical adult in the United States, that mass is a little bit higher. So you can expect that our bodies, like a typical adult body, will have somewhere a little bit more than 8 pints. So say if you weigh 150 pounds or something, you might have 10 pints of blood in your body, right? If you weigh a little bit less, then you might have 7 pints or something like that in your body. Your heart might be a little smaller, and you might be a little bit less blood out per heartbeat. Bottom line is, we just figured out, wait a sec, about 10 pints of blood gets pumped every minute in an adult, and you have about 10 pints in your body. So this person, this relatively light person, a light adult, I should say, compared to the typical United States adult mass or weight, has a little bit less than 10. So we typically, adults might think we might have about 10 pints of blood. So about the same amount of blood that we have in our body goes through our hearts every minute. Now, not all the blood is perfectly efficiently removed all the time, right? Some of the blood pools once in a while, unfortunately. It doesn't always move perfectly smoothly. If you don't have perfect circulation, sometimes you have issues. If you have a bruise or something like that, some of the blood pools, etc. But the bottom line, overall, right, difference between 8 or 10 or 12 or something like that's not a whole lot. It's a few percent, 10, 20%, something like that. But realize that physically speaking, your heart is pumping about your entire body's worth, your entire body volume's contents of blood every single minute of your life. And it's pumping it at this pressure of 100 millimeters of mercury, and then 120 or so, or 80 after the pump, right? Pump 120, relax 80, 120, 80, something like that. And so you have this continuous flow out of your heart through your arteries into the rest of your body, right? And then you know about how veins basically carry the blood back to your heart. And that's at a lower, more steady pressure because the arteries are the ones that get it out. And then you have to get it come back to your body. And coming back to it is a little bit harder because the pressure is lower, right? So the return is a little bit more challenging sometimes. For example, from at the bottom of your feet, right? Now remember, this force pressure area thing, you want to be able to get force into your blood pumping, right? So you got to be able to find a way to get into your blood. Let's say you are trying to push some medicine into your body via a hypodermic needle, right? What pressure do you need to get it through your skin and into your muscle tissue? Some sort of vaccination, or maybe some other kind of whatever thing you need to put in, right? How about a drip? If you have an IV bag, right, and you want to drip it into your body, it has to have enough pressure when it reaches your veins that it's going to go in to your blood system. If pressure is too low, it won't flow in, right? Because that pressure is pushing outward. So you need to know what the pressure is of the veins in your body in order to get it vein. That's why you don't put, for example, a hypodermic injection into an artery if you can help it, right? Because first of all, when you puncture the artery, then you get extra bleeding. That's just not good because you don't want that. The other thing is the pressure that you have to put into the artery is like way higher than the pressure that you need to put into a vein. That's why you're always looking for veins in order to put either the hypodermic injection or a blood thing or an IV tube into your body. You need that lower pressure. Physics, pretty cool, right? Okay, so this is our general conversation about blood pressure, and we'll get into some specific details in a moment. I'm going to show you in the college physics textbook some more information that I recommend you read, and I welcome that you think about some more, because we'll get into specific examples later, all right? So let's just get started. We'll go back to the college physics textbook in the OpenStax series, right? There again is the URL, which is great, and here's your table of contents. If you go into the table of contents, okay, and you go down to chapter 11, fluid statics, there's all kinds of good stuff here. We've already talked about fluid statics, right? What is a fluid? And then density we've talked about, right? Density is the mass divided by the volume, right? And usually the units are in kilograms per cubic meter or something like that, or grams per cc, whatever you choose. And then here's pressure, right? Pressure. I'm sorry, I just, singing that song because it's great. And then there's also a song by what's his face, Billy Joel, pressure. Anyway, so here's pressure, force divided by area. We've been talking about before, 1 Pascal, 1 Newton per square meter, right? And then there's the units of millibars. This is from meteorology. This is like weather reports, right? What's the atmospheric pressure? 1 millibar is by definition 100 pascals. So that's kind of something that we use sometimes, not so much. Aha, here we go. Force small pressure, force large pressure, because the needle is smaller, the area is smaller, and so you don't have much. While the person being poked with the finger might be irritated, the force has little lasting effect. However, the same force applied to area the size of a sharp end of a needle is great enough to break the skin, and then you can get the good medicine into your body that you need. right? So you can figure out the air pressure, what forces pressure exert, and you can multiply the force equals the pressure times the area, and then you know how much the force is, how much and so these are all very useful. And then pressure is exerted on all sides when you're under the water. So your eardrum there gets pressure from the water around you. Okay, and there are lots of really neat things, and we haven't even talked about gas pressure yet. That comes next. Gas pressure is really cool. You may have heard already about something called PHY, right? The ideal gas law. It's usually taught in chemistry classes for some reason, but believe me, it's physics. And I want to make sure that you understand how the physics of that works. Now, the variation of pressure with depth in a fluid, the section 11.4, you don't have to worry about too much. All right, a little bit, but too much. So you can glance through it and kind of absorb it a little bit. Do not worry too much about it in terms of calculations, but understand how this works because, of course, we breathe the air, we live on the earth, and we swim in oceans or in pools. So it's worth knowing, but you don't have to worry about the computation. Pascal's principle is super cool. Again, not something you need necessarily to use in your class as far as this class is concerned, but doesn't mean you shouldn't learn it because it's fun. All right, so I want to make sure to sort of understand it. A change in pressure applied to an enclosed fluid is transmitted to all portions of the fluid and the walls of its container. That means, let me just stop sharing for a moment and sort of just illustrate what that means here. If I blow on a balloon and it has a certain pressure, the pressure of the air inside the balloon pushes on every part of the balloon the same. The pressure is the same everywhere. Isn't that cool? Yeah. You don't necessarily think that that's true, but it's true, right? So that's really important to understand. And it's really kind of fun when you're doing things like, engines and things like that, pistons and so on. And we don't have to worry too much about that, again, like I say, but I want you to be aware of its existence because it's worthwhile. Knowing this means that you'll know like how your power brakes work or how your power steering works in your car, right? The hydraulic systems and things like that, brakes, power brakes, these things, they're all part of that. And so I want you to sort of know it, but don't, again, worry about the computation of it, all right? And then this, though, 11.6, make sure you understand this. What is a gauge pressure? What is an absolute pressure? It's sort of words, but they're kind of useful to know, right? And how that happens to be measured. And here's your atmospheric pressure, here's your meter stick, different ways of measuring. And here we are. Dun, 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 1 millimeter of mercury is 133 pascals. It's that conversion factor. And then blood pressure. Okay, sorry. Systolic pressure, the big one, the number on top, the diastolic pressure on the bottom, right? And here's the example of a blood pressure cuff. So you have a number, like we said, 120/80, for example, is something that's considered generally healthy among typical adults. And then, here's a cool one. Remember talking about the IV drip? I want you to take a look at this and see what happens. Notice you have to hold, right, an IV bag up. Why do you see in the movies or say you're in a hospital or something and notice that the IV bag, right, dripping an intravenous, like going into the vein, intravenous drip, right, is held up high above the person? Why is that? I mean, yeah, it makes some nice decoration in a movie or something like that, but why is it actually there? It's because you want to use the force that's generated by gravity in order to create a pressure that will get the liquid into the veins. So you see here, this particular problem is hypothesizing if you have to get 18 millimeters of mercury above the atmospheric pressure in order to get the IV dripped stuff into the vein, because the pressure outward, presumably out from the vein, is a little bit less than 18 millimeters of mercury. Okay, and therefore you have to drip it at least 18 millimeters of mercury for it to get in. Okay, so you have a little the density of the fluid, which is like water in this case, 1 gram per millimeter, okay, gram per cc. Like how high do you have to hold it up in order for this to be able to go down and create that pressure that allows you to get it in to the body? All right, so you use these numbers, the height multiplied by the density of the fluid, multiplied by the gravitational constant acceleration at the surface of the Earth, hg rho, or h rho g in this case. And then you do the substitution. Turns out you got to hold it up about 24 centimeters. That's about 10 inches above where the thing goes. So there you have it. Now you know it's the physics. It's not the chemistry. It's not the biology. It's not the anatomy that makes you have to hold the IV bag up. It's physics. And now here's all the conversions that I was talking about earlier. There's plenty of good conversions that you can play with and have a good time with. All right. So that's the kind of thing I want you to see. And then here, Archimedes' principle, again, fun stuff. All right. Buoyancy and things like that. But again, don't worry too much about it. I want you to read through it and learn it because it's cool, right? Why does a battleship float, right? Why does a small piece of metal sink? And it has to do with relative densities. It has the, how much is floating, whether you're in it, sitting down, and whether you're going up, going down, you're measuring like your body mass index, or your percentage of muscle or fat or protein or bone you have in your body and things like that. And then the classic example of trying to figure out whether or not you actually have a certain metal, right? A certain amount of material that is actually pure silver or pure gold. You can use that to figure out those things. So that's cool. And don't worry too much about having to deal with, again, memorizing it or learning it, but it's kind of cool to read. Finally, this cohesion and adhesion in liquids, this has to do with surface tension. Don't even worry about this. I want you to read it, but glance through it. I'm going to have a little tiny thing in the study guide so that you can know about it. But again, as long as you're aware of it and you've read through it and understand it, move on. Okay, that's where we're going. Finally, this section, 11.9, pressures in the body. Look at all this good number stuff. We are going to go into much more detail on this stuff in the next lecture as we talk about various fluids and ideas about blood pressure, or pressure inside the eye. You've heard of glaucoma before, right? Or how about pressure in the ear, eardrums and things like that, equalizing pressure. That's gas pressure now, as well as liquid pressure. So we got lots of cool pressure things to be thinking about. Ooh, and then there's the chest cavity between the lungs and the ribs. In a moment, when we go to the next vital sign, right, of the 4 big vital signs, respirations, how often is someone breathing? I'll tell you about that pressure changes, and that's not liquid pressure, but that's gas pressure. So we got this blood pressure, and then remember we're talking about like blood pressure in veins. Remember just earlier, the example, right? Blood pressure in veins ranges up to about 15 milligrams of mercury. And that's why in that example earlier in chapter 11, it's saying, let's say you need at least 18 millimeters of mercury in order to get it in. It's because it's a little bit higher than 15, right? So that's how that all works. This is physics in the body. It's the pulse, right? How much volume is being pushed out and at what pressure. And then you have the systolic and the diastolic pressures, and we can talk all about that stuff physics-wise later. Now, the blood pressure, right? You have high blood pressure, low blood pressure, things like that. Those are all useful and interesting stuff. That's all like the physical diagnostics, but now you know, right? And I hope you've been writing this all out. You've been taking notes about this in the study guide. I hope you've been doing that. If you haven't, get into that. You can make that happen, go to later, and then go back in the study guide and read some of the stuff. I'm talking about like what you need to read and give me some basic points about what pressure is like and what it means to talk about fluid pressures and things like that, because that's really key in our understanding of the physics of the human body as we go forward. Okay, so bottom line, physics, pressure, heartbeat, force, causing blood pressure, systolic, diastolic, millimeters of mercury, right? Atmospheres, pascals, all those cool things. Have that rolling around in your head as you're doing the study guide. And I will see you in the next lecture when we talk even more about this. And now we're going to talk about gas pressure and respiration. Oh, it is so interesting. I think it's super duper cool. And if you know how this works, this is going to be a pretty powerful thing for you to have as you move forward in your academic career. Okay, thanks so much. We will talk again soon. I really appreciate your being here. We will talk in the next lecture. Thanks again. Talk to you later. Pressure, pressure. Under pressure.